So let's talk about power distribution in a parallel circuit. When we talked about series circuits, we saw that the power applied to a resistive circuit equals the power dissipated by each of the elements. And we just saw that that was a simple sum, right? The sum of the power absorbed by the resistors was the power delivered by the source. The same is true for our parallel circuit. As a matter of fact, any network composed of resistive elements, the power applied by the source equals that dissipated by the resistive elements. So basically that means the power we apply has to be absorbed somewhere inside the circuit. So let's work through an actual example here. And we're going to just solve this like we did our other parallel circuits. So the first thing we're going to do is find our total resistance, and you can be working through this with me. We've got 20K and 56K. So our RT would be 1.44K. And then that will give us our source current, which should be about 19.4 milliamperes. And I'm going to go ahead and draw this into the circuit as well. Always helpful to have at least your currents and your voltages noted in the circuit. Now remember also, our R1, R2, and R3 are all in parallel with the source. And the important thing about that is that we know we've got 28 volts across each resistor, and that will allow us to find the current through each branch of our circuit. So I1, of course, is V1 over R1, which is 28 volts over 1.6K, or 17.5 milliamps. So we've got 17.5 milliamps here. And then our I2 is V2 over R2, or 28 volts over 20K ohms of resistance, which is 1.4 milliamperes. And then I3, which would be V3 over R3, or 28 volts divided by 56K, or about half a milliamp, or 500 microamps if you want to use the correct engineering notation here. Let me see if I can move this just a little bit. Okay, so we have half a milliamp there. Now, remember, our current coming into our branches has to equal the current leaving the branches. So 17.5 milliamps plus 1.4 milliamps plus 0.5 happens to equal 19.4. So as you're working through this, you can be doing these calculations and check behind. So how do we calculate the power delivered to our circuit and the power absorbed by our resistors? Well, remember, that is just P equals V times I, okay? So the power delivered to our circuit is that PE, and it is the source current times the voltage we're supplying to the circuit. So if we're supplying 19 milliamps of current using a 28 volt source, we have about 543.2 milliwatts. Okay, I think that was supposed to be 0.4 here, in case you're following along. And now let's find the power delivered to each of our resistors. So PR1 is going to be V1 times I1, where we still have 28 volts we're supplying to a 1.6 k ohm resistor, and the result is 17.5 milliamps. So that means we've got 490 milliwatts of power there. And I'm just going to make a note of this. So we're supplying 543.2 milliwatts here. We're absorbing 490 of those milliwatts right here. And let's look for PR2, which is going to be the voltage drop across R2 times the current through R2. So 28 volts times 1.4 milliamps, or 39.2 milliwatts again. And then for the power delivered to R3, that's again 28 volts because it's in parallel with my source, times the half a milliamp there. So we've got 14 milliwatts there. Now, what we're saying here is that our 543.2 milliwatts should equal 490 plus 39.2 plus 14 milliwatts. And so we're just going to check it. 490 plus 39.2 plus 14 gives us 543.2 milliwatts, and it does add up. So power distribution, whether it is in series or parallel, the power you supply to your circuit in watts is equal to the power absorbed by all of the resistive elements in the circuit, whether they're in series or they're in parallel. It's just a simple sum at that point.